this video, we're going to be looking at the energy relationships of a mass spring system as it oscillates in simple harmonic motion. A mass spring system consists of a mass that is attached to a spring. When you stretch or compress a mass spring system, you give the system potential energy. And this kind of potential energy is called elastic potential energy. And the elastic potential energy stored in the spring is equal to the work done to stretch or compress the spring. Let's look at the concept of work. Suppose you wanted to calculate the work done pushing a crate for 5 meters. If we applied a constant force over this 5 meters, the work done would be F times D, 20 times 5, or equal to the area under the curve, which is 100 joules. However, Hooke's law tells us that the force needed to stretch or compress a spring is not constant. It takes more and more force to stretch the spring a greater distance. The work done, though, is still equal to the area under the curve. So let's talk through this derivation. So if the work is equal to F times D, or the area under the curve, in this case, the area under the curve is a triangle. So it's going to be 1/2 the base times height. So 1/2, the base is going to be X, how far we stretch it. And the height is going to be the restoring force needed to do that. So when we go to the next step, we know that the restoring force is equal to Kx. So we replace the restoring force with Kx, and we can see that the work done to stretch a spring is equal to 1/2 Kx squared. And the elastic potential energy is equal to the work that was done. So we now have derived the equation for the elastic potential energy that is stored in a stretched or compressed spring. Conservation of energy also applies to a mass spring system oscillating in simple harmonic motion. When we had a roller coaster coming down from the top of the hill, we could say that the total energy at any point would be equal to the potential energy that it had and the kinetic energy that it had. When it was at the top of the hill, all of the energy was potential, so the total energy was equal to mgh. And then all that potential energy turned into kinetic energy at the bottom of the hill. We have the same sort of thing happening with a mass spring system, perhaps oscillating vertically in this example. So this is the natural length of the mass spring system. Here it's compressed, here it's elongated. But it doesn't really matter where the mass is in its point of oscillation. The total energy is always going to be equal to the potential energy plus its kinetic energy. So 1/2 Kx squared plus 1/2 mv squared. When it's compressed, when we're at an end point, all of the energy is potential because our spring fact tells us that we have no kinetic energy. So the total energy in this case would be equal to 1/2 Kx squared because I have no kinetic energy. When I'm at this stretched endpoint, the same thing is true. But at equilibrium, all of the energy is kinetic because I'm at maximum velocity and I don't have any potential energy. So at equilibrium, we could say that the ET is equal to 1/2 mv squared. So what would a graph of these energy exchanges look like? On this slide, we're talking about a mass on a spring that's oscillating in simple harmonic motion, and we're asked to sketch energy versus displacement graphs. The first one we're going to be doing is the potential energy versus displacement. That tells me that displacement has to be on the x-axis. So it doesn't matter whether this system is oscillating horizontally or vertically, the graph is going to look the same. So I have my system oscillating between x min and x max, which tells me that halfway in between has to be equilibrium. Now I'm just going to think through this. What do I know about potential energy at equilibrium? Well, I know that the potential energy is 0, and I know that it's a maximum at x min and x max. So I know these 3 key points, and that's all I need. So the mistake some people make is they just connect to the dots. And they make a graph that looks like a V. It's not a V. And we know that because potential energy is 1/2 Kx squared. The squared means it's going to be parabolic. So this is what the graph is going to look like. When I get to the kinetic energy graph, it's just going to be the reverse because I know that at equilibrium, or kinetic energy is at a maximum, and at the endpoints, x min and x max, kinetic energy is 0. If I want to draw the total energy graph, it's just going to be a straight line going across. But many times we graph the potential energy graph and the kinetic energy graph on the ET graph, because this can show me that, for example, if my mass was, let's say, located over here, you can see that I have a little bit of potential energy. I have a lot of kinetic energy. And if I added up those potential, or that potential and that kinetic energy, it would equal ET. Sometimes we're asked to sketch energy versus time graphs. Energy versus time graphs are always sinusoidal and are always positive. I'm going to get the potential energy graph from the displacement graph, and I'm going to get the kinetic energy graph from the velocity graph. So let's look at this. Here we have a displacement graph that shows one period of oscillation, but because potential energy is equal to 1/2 kx squared, anytime I have a negative displacement, I'm going to end up squaring it and it's going to turn positive. So it's going to take this negative dip here and flip it positive, and I end up with two positive curves instead. Same thing with the velocity. So here we have a velocity graph that shows one period of oscillation, and I have some negative velocities. But because of 1/2 mv squared, I'm going to square those velocities and they're going to turn positive. So I can flip them up, and you can see that the graph ends up being all positive. And the total energy graph is always going to be positive and just a straight line. Let's look at an example problem that has a little bit of everything in it. A 200-gram mass is attached to a vertical spring with a spring constant of 178 newtons per meter. The spring is then stretched 15 centimeters and released. Letter A says, what is the amplitude of oscillation? Well, if I stretch it 15 centimeters, that is the amplitude of oscillation. I just turned it into meters, and the amplitude 0.15 meters. Letter B, determine the maximum potential energy of the mass. So let's use our potential energy equation. Potential energy is 1/2 kx squared. We have 1/2 times 178, and our x, we know that potential energy is a maximum at an end point, so I just made sure that I put in the maximum displacement, and the potential energy at the end point is 2 joules. But we also know that at the end point, there is no kinetic energy. So that tells me that the total energy of the system is 2 joules. Part C says, what is the maximum velocity of the mass and where does that occur? So maximum velocity happens at equilibrium. To find the maximum velocity, we have to think through this energy. So we have a potential energy of 2 joules at the end point. All of those 2 joules are going to turn into kinetic energy joules at equilibrium. That's kind of like a roller coaster, has gravitational potential energy at the top of the hill, and then all that potential energy turns into kinetic energy at the bottom of the hill. So our 2 joules is going to turn into kinetic energy. So there's my 2 joules equals 1/2, which I just wrote as a 0.5. The mass was 200 grams, so I turned that into 0.2 kilograms, and then I'm just solving for V, and we find out that the maximum velocity, 4.47 meters per second, is going to be the speed of the mass as it passes that equilibrium point. Letter D, what is the velocity of the mass when it is 5 centimeters from equilibrium? So at part D, I am not at an end point, I'm not at equilibrium, so now I'm going to use the concept of conservation of energy, that we know that the total energy is going to be equal to the sum of the potential plus the kinetic. The potential is 1/2 kx squared, kinetic 1/2 mv squared, and we know that the total energy is 2 joules. So where am I? I'm 5 centimeters from equilibrium. So I do have a little bit of potential. So 1/2 times 178 times 0.05 squared. I turned that into meters. And then 1/2 mv squared, and then I just solve for v. So we can use the concept of conservation of energy to find the position or the velocity anywhere in the system. Letter E, how far is the mass from equilibrium when the velocity is 3? So now we're kind of doing the reverse, where we have, we have the total energy is 2 joules. This time we know the velocity, and we're solving for the position. And we find out the position is 0.11 meters, which means we're 11 centimeters from equilibrium. So we're not at equilibrium, we're not at 0.15, but we're at 11 centimeters, and we have a velocity of 3. So letter F says, sketch energy bar graphs for the mass when it is at x equals 15. So that's going to be at an endpoint. X equals 0, that would be equilibrium, and x equals 5 centimeters, which is partway between equilibrium and the endpoint. So before we can talk about how to draw an energy bar graph, let's do a little bit of organizing first. So we know down here when we are at an endpoint that all of the energy was potential and we had no kinetic energy. So the potential energy turned out to be 2, we had 0 for kinetic, and then we found out that the total energy of the system was 2 joules. Then when we're back up here to equilibrium, we can do the same thing. And at equilibrium, those 2 joules turned into kinetic energy. So now the kinetic energy is 2, and the potential energy is 0, and the total energy obviously still 2. And then when I'm at 5 centimeters, let's do the same thing. Now we know that we have a little bit of potential energy, 1/2 kx squared. So we can put in the 5 centimeters and find out that our potential energy is 0.22 joules. And we did solve for the velocity, which was 4.22, so we can use that to calculate our kinetic energy joules, 1/2 mv squared, and I got 1.78. And then I can kind of check my answer by adding these two together, and it does add up to 2. And just a little FYI, sometimes when you add them up, it doesn't add up, and that's just round off error. But by writing it this way, it's going to help me organize my thoughts when I get ready to do my energy bar graphs on the next slide. So I organized these calculated values down here so they are easy to see when constructing the energy bar graphs. So an energy bar graph is a bar graph that shows each type of energy on the x-axis. So this graph shows the potential energy, kinetic energy, and total energy of the system when it is at x equals 15. This set of bars will be for x equals 0, etc. The next thing we need to do is scale the y-axis. I can see that the total energy is 2 joules. So we'll make the y-axis go up to 2 joules. Halfway will be 1 joule, and then we'll just scale it. We'll call that 0.5 and 1.5. Next, we're ready to graph the data, which really means shading the bars. So we're going to start when the mass is 15 centimeters from equilibrium, when it's fully stretched at an end point. And we know that we have potential energy of 2 joules and total energy of 2 joules. So I shaded the bars all the way up to 2 joules, and I left the kinetic energy blank. When the mass swings back to equilibrium, you can see that we have still total energy of 2 joules, but all of that potential energy now has turned into kinetic energy. And then when we get to the final one, where we are partway in between, we have a little bit of potential, 0.22 joules, and the kinetic energy, 1.78 joules. Now this is why it's important to scale your y-axes and to draw your graphs very carefully, because what someone's looking at is if you took this blue bar and you put it on top of the yellow bar, would it be the same height as the green bar? We want our energy bar graphs to visually prove that conservation of energy is holding true. One last topic we should discuss is damping. Damping occurs when an oscillating system loses energy over time. And because energy is closely related to amplitude, we can recognize energy loss if the amplitude of a wave decreases over time. The energy loss may be due to a variety of factors, but air resistance and friction are common examples. These first two images show damping occurring in an oscillating system. This last picture shows damping of maybe a bouncing ball. In each case, though, it's important to see that the frequency of the motion does not change. The ball still bounces at the same rate, and the system continues to oscillate with the same period.